Okay, welcome to Math 408, L functions and sphere packings. So today we're going to talk about lattices and try to answer some of the questions we have about the vector distributed. So why do we care so much about how vector lengths are distributed? Where have we seen the importance of this?
In our sphere packing?
Somewhat in the sphere packing, but we've seen it more recently in the past week. When we were trying to construct a modular form, we saw that there was a problem if we could keep mapping an element and get a sequence of elements that were converging, which is equivalent to saying we have a sequence of points that would be converging to the origin. All right, so I'm going to be starting to follow a little bit more detailed notes from my colleague. We're moving over to his part of the course. And so we will live in Rn from now on. Often n equals 2. And the hope is that if we just do the calculations in 2 dimensions, you can see that by just using linear algebra, it's essentially the same calculation in general. But given my difficulty in drawing, let's keep things to a 2-dimensional argument. So we take a basis B of Rn, V1 to Vn. And I will put arrows on them just to remind us that it's a vector. What must be true about all bases of Rn? Same number of elements. So every base has the same number of elements. This is a result that was hopefully either proven in linear algebra or at least stated explicitly in linear algebra. And then we can look at the set of all points, RV1 plus dot 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 plus RVN. And what should that equal?
Rn.
That should just equal Rn. And further, everything in here should be unique. We should never be able to get the same element 2 different ways. Okay. Standard results. We can now look at the lattice, lambda b, and I'll put a b there to remind us that it's coming from the basis, which will be zv1 plus zvn. And so we're looking at just integer multiples. And then this has a lot of nice properties. It's a free abelian group of rank n. So the first question you ask is whether or not a basis is unique. So what's the answer? Okay, so I'm seeing at least one no that bases are not unique. Can you give me an example of another basis for V1 and V2?
V1 plus V2, V2.
V1 plus V2 and V2. What about 2V1, V2? So the question is basis for what?
Well, they don't give the same lattice.
So all bases for R2 not the same lattice. Well, let's think about it. To some extent, I give you any 2 vectors, and they're going to be a basis for R2. So any 2 linearly independent, of course, and we have standards in this class. Yeah. Any 2 linearly independent vectors will give a basis for R2. So if I ask, is this another basis? It's really not an interesting question. What is the interesting question is it a basis for the same lattice? So would this be a basis for the same lattice?
Yes.
What about this one?
No.
Okay, so we put a big X there. why does this work but this doesn't?
We can't recover V1 from the last one.
So we can't recover just V1 from this. Is there any way to try to associate something to the lattice that might allow us to tell when two different bases have a chance of giving the same lattice? They may not give the same lattice, but is there some quantity that we could associate that would give us you get a chance?
Eisenstein series?
So that's a bit involved. I like the atomic bomb approach. What else could you do? Is there anything lower level that should be maybe the same as you move from basis to basis?
Matrix transformation, if you can transform an SL2Z.
Okay, so one question is, if I have V1, V2, and W1, W2 bases for some lattice lambda. Let's see what that would mean. Well, clearly, we could write W1 as maybe AV1 plus BV2, and W2 as CV1 plus DV2, with A, B, C, D living where?
In Z.
In Z.
So this is SL2.
Okay, so there's a claim that's in SL2. What is SL2Z?
Yeah, GO.
Well, you need AD minus BC.
Right, so do we know that AD minus BC equals 1? So we clearly know we have this. We also have V1 and V2 can be written as alpha W1 plus beta W2, gamma W1 plus delta W2, alpha, beta, gamma, delta are in Z.
Yes, because the matrix is invertible, and its inverse has entries in Z.
Excellent. So claim A, B, C, D is an SL2Z. And of course, if that's an SL2Z, by just changing the roles of V and W, we clearly have the other. Okay, so how did you get, we know W1, W2 was A, B, C, D of V1, V2, and V1, V2 is equal to alpha, beta, gamma, delta of W1, W2. So what do we now get? So you basically got it.
Well, ABCD inverse is alpha, beta, gamma, delta.
So one is, you could say A, B, C, D inverse equals, so one is A, B, C, D inverse equals alpha, beta, gamma, delta. Yes?
So this is going to give us that the determinant is plus or minus 1.
It's going to be plus or minus 1. That's fine, because what we can do is we can basically say, screw it, let's go to PSL2Z and not worry about, oh wait, well no, sorry, that would not be enough because that would still be minus. But of course, we should expect something like that, because if I take one of my basis vectors and I just take the negative, it's clearly going to generate the same lattice. If we replace V1 with negative V1, we can remove the negative and incorporate it into the integer Z, and so it's the same lattice. So that's not a big deal. So it's too strong to say that it has to have determinant 1, unless we somehow specify some kind of orientation or something about the vectors. Up to something of determinant negative 1, flipping the sign of something or something like that. All right, so how does that help us now? Okay, so let's do it this way. It's been a long time since I've done that. What's the inverse?
It's
1 over AD minus BC,
D
negative C. Okay. If you multiply this by AB, CD, AC, when you hit that, we'll get AD minus BC, that which will be 1, and then BD cancels, so that is correct, equals alpha, beta, gamma, delta. Right, how does this help us? You're trying to show that the matrix has determinant plus or minus 1. Yes?
So we know that D is an integer, we know that alpha is an integer.
Yes.
So D over AD minus BC equals alpha.
Okay,
AD
so
minus
this
BC
gives us D over AD minus BC equals alpha is in Z.
Wait, don't we know that AD minus BC is 1 is a determinant?
We don't know that yet. We just know that there's some choice A, B, C, D. This is the whole point for the lecture, or this is one of the points for this part of the lecture. How easy it is for you to accidentally assume something. It's very easy to just naturally assume, oh, of course that has determinant 1. We have to prove it. So we know D over AD minus BC is an integer.
Similar, we can show that AD minus DC divides A, B, C, and D.
Okay, so what do you want to do now?
We can do the same equation for B to beta, C to
Okay, so we get negative B over AD minus BC equals beta is in Z. You may be enjoying this at home, you may be enjoying this in your seats. I am not looking forward to writing this algebra nightmare. So we now have to start going to, well, what would happen if the determinant wasn't 0? I'm sorry, wasn't 1 or negative 1. Then it would have to divide D, so D would have to be multiple. So we could start going, well, let's let D equal D tilde times the determinant of A. And then similarly, negative B would be negative B tilde determinant of A. Negative C would equal negative C tilde determinant A. And then A would equal A tilde determinant of A. Yes?
So now we can now take the determinant of of A inverse,
Right.
and we're going to get, or just the determinant of A, I guess. And it's going to be determinant of A cubed or something. It's not going to be pretty.
Well, the question is, what is the determinant of this quantity?
Isn't that just like, so we have two integer matrices, so they both have to have integer determinants. They're multiplicative inverses to each other, and the only integers whose multiplicative inverse is also an integer.
Yes. And so that means going back up to what we have over here, take V1, V2, and look at what's written right next to it. If we try to take the determinant here, the determinant of this is AD minus BC. That doesn't cancel with this, because we're multiplying this by every entry. So if you multiply every entry by this, you get this coming in as a squared. So if I try to just now put in the determinant of A, if I pull that out, it would come out as a determinant of A squared, cancels this one, and you have determinant of A times A tilde, B tilde, C tilde, D tilde. So this is not a bad thing to try to see if you can make the algebra work. There may be a way to do so. But again, I really care more about thought processes and why do you go down certain paths and not others. So this was deliberate. Sometimes I don't do things deliberately. This was deliberately writing them next to each other. And now we get W1, W2 is A, B, C, D, alpha, beta, gamma, delta, W1, W2. So this has to be the identity matrix. And because their determinants are inverses of each other, you get the determinant of A is equal to could it be plus or minus? No, it has to be,
1 over determinant.
it's got to be 1 over the determinant of the other one. 1 over determinant, we'll call it Greek A. And they're both in integers. So you need a number, an integer, that's reciprocal is also an integer. Therefore, determinant of A equals plus or minus 1. And that finishes the argument. So I think I've probably remarked that when I was an undergraduate, I was taking a complex exam, and after 2+ pages of tedious calculations, I wrote, there's got to be a better way of doing this problem. And the professor wrote in the margins, it's about time you realize that, Steve. So sometimes it's not bad to try and see, can you do a calculation? Can you just brute force it to death and get it to work? But at the end of the day, do you have a deep sense of what's going on and why? And so here, when we think about what's going on, we've got to be able to go back and forth. If they're each a basis, I've got to be able to go from the V's to the W's or the W's to the V's. Is there anything about this that crucially used n equals 2? No. So true for all n greater than or equal to 2. And I'm not sure if I've said this explicitly, but part of our definition of what a lattice will be is that it has to have rank n in Rn. So we will not allow the two vectors to be along a line and give us a degenerate lattice. This is similar to, do you consider the following a triangle? Where you choose 3 collinear points. I don't want to consider that a triangle. Okay, whoops. My daughter's just at a doctor's appointment, so just keeping this open. Okay. Any questions about this? So can we come up with something that might be invariant as we go from one basis to another?
The determinant of the vector, like the matrix of the vectors.
Okay.
Like, is one of the lattice invariant?
Well, I'm making it completely open. So I would love an easy way to tell if V and W can or cannot be equivalent. So just 1 second. So we've already shown right now that if they're both bases for lambda, they are equivalent under a matrix in.
I thought this was, if we're trying to get the same lattice, I don't think this is true for any two bases.
Well, okay, we want bases for the same lattice. Okay, so no, I want to make sure I haven't confused anything. So we want them to be bases for the same lattice, and the lattice is going to be integer multiple, linear combinations over the integers of our vectors. And so if 2 pairs generate the same lattice points, we've just shown that there has to be an invertible matrix in plus or minus. And we can assume that the determinant is 1 if by necessary reordering W1 and W2. Because if we have a transformation, reordering them will change the, what reorders them? If I give you 0, 1, and 0, I think. If I do something like that, that should flip things. So we should be able to assume that the determinant now is plus 1. Okay, so if you have the same lattice, then you are equivalent under one of these matrices in GLN, actually not GLN, SLN. If you are equivalent under matrices, under a matrix in SLN, do you generate the same lattice? What about the other direction? If there exists a B, C, D in SL to Z such that W1, W2 equals A, B, C, D, V1, V2, is it the same lattice?
Yes, because you can just write W1 equals AB1 plus BB2.
Yeah, its inverse is also integer value.
Its inverse is also integer valued. So we would get A, B, C, D inverse W1, W2 is V1, V2. So in particular, we'll have something like alpha W1 plus beta W2 is V1, gamma W2 plus delta, gamma W1 plus delta W2 is equal to V. And now if I want to take something in the original basis, if I had, m copies here and n copies here, and now I have it written in terms of the w's. Conversely, if I have something in terms of the w's, it's even easier to get in terms of the v's, because I can write the w's in terms of the v's. Okay, so the matrices that we've been looking at, these SL 2Z matrices, are extremely useful for questions like this. So hopefully now we have a decent sense of when two linearly independent vectors generate the same lattice when we look at integer linear combinations of them. So my question is there any way to quickly look at V1 and V2 and try to get a sense of when they could generate the same lattice?
Well, if they don't have the same determinant, then they don't generate the same.
Okay, so here is a great claim or conjecture, depending on whether or not it turns out to be true. So V1, V2 and W1, W2 generate the same or maybe for this to generate the same lattice, we need V1, V2 as a matrix like this to be the same as W1, W2. Yes?
I think trivially we're going to need to add absolute values.
Yes.
Yeah.
Up to sign. Yes. Do you know about the rationalized MKS units? Does everybody know about the metric system?
Is that where like G equals 1?
Yes. So the gravitational constant equals 1. Speed of light equals 1. I think there's one more that you said equal to 1.
Coulomb's constant, maybe?
I think it's Planck's constant. I think, I'm not positive on this one. This is the rationalized MKS. Now the fine structure constant is fascinating because it is independent of the units. It's a dimensionless quantity. It has real significance. So read about alpha, which is approximately 1 over, I think, 137, the fine structure constant. For a while, people thought it might actually be exactly 1 over 137, which would have had really interesting consequences if it's exactly 1 over prime. But what's nice about something like this is you don't have the man-made units coming into the equation. The problem for me is when I look at equations like this, I lose the physical interpretation of being able to just quickly look down and see what something is. So over here, in mathematics, we don't have the rationalized MKS units. We do sometimes have pi equals 2 pi equals 2 pi I equals 1. Now, obviously, of course, this can't be true. What class would that be a useful thing to have? Engineering. Applied math, but there's a really important one that I know at least 2 people in the audience should be able to hammer out right now. Complex analysis. When you're doing the contour integrals and you have these 1 over 2 pi I factors. Oh, don't worry about it, it's just 1 now. But for a lot of problems, it's nice to be able to see these factors so you can get a sense of what's going on. So you'd mentioned Coulomb's constant. How do you write Coulomb's constant? Do you write it as like 1 over 4 pi epsilon naught? Oops. It's been a while since I've done this too. Why do you write it as 1 over 4 pi? Why would you do that to yourself?
So you don't want to write 1 over 10, I don't know.
But why 4 pi? Surely there's a reason we're doing 4 pi. Yeah, it's a sphere of radius 1. It's related to the surface area of a sphere. And if you think about problems in 3 dimensions, if you have a source at the center and has a constant yankage, and that yankage is being split over a sphere, then the force should be going down. I first heard this argument in one of Feynman's lectures on physics, that the force should be going down proportional to the radius squared because the surface area is growing like 4 pi radius squared. And then if it goes down like 1 over r squared, you have a constant net push inward, just being distributed over larger and larger regions. In a 2-dimensional world, you would actually expect gravity to fall off maybe as 1 over r, in which case it's now infinite work to move something to infinity. So it's worth looking at how we choose to define constants and terms. The 4 pi in the Coulomb's constant is to actually indicate spherical geometry. For the most part, however, as a society, we have decided to embrace pi, but there is a small subset of people who want to celebrate what day? Tau Day, twice pi. And when you look at a lot of stuff in complex analysis, there is a legitimate case to make that 2 pi is the fundamental object and not pi. Everything we do in Fourier analysis, it's either the 2 pi I. Okay, so up to sine, the conjecture or the claim is that if they are going to generate the same lattice, they must have the same determinant. Do we have a fast proof of this?
Yes, you can just multiply by something in PSL2Z.
Okay. And do we know that there's something that in PSL2Z that we can multiply by?
Yes, because we just proved that.
Yeah, we just proved that they have some matrix in PSL2Z or maybe SL2Z up to, we don't really care about sign, such that it has determinant 1, and we know B1, B2, and then we'll do it as A, B, C, D is W1, W2. And now how do we want to view this? Because I want to be able to then claim the determinants must be the same. And you may have noticed I've been a little bit fast and loose sometimes with the mathematics. This is a vector
Yeah.
with two components, but what are the entries of that vector?
They're row vectors.
They're row vectors. So we could really expand this out. We could have AV1 plus BV2 equals W1. And I could write this out the long way as this is AV1x plus BV2 x equals W1x, and then AV1y plus BV2y equals W2y. And then we can do the rest for the other two. We would similarly get, that would be, I think, C V1x plus D V2x. Oh, sorry, this would be W1y. It would be W2x, and then C V1y plus D, and these no longer have arrows, plus D V2y equals W2y. All right, I will try to keep that on the board because that's such an important result. How does this help us collect things? Do we want to have our V matrix, V1x, V1y, or do we want V1x, V1y down there? Which way do you want to do it? And if you're not sure, we've got a 50-50 chance. Which way? That one? All right, so you want to do V1x, V1y, and then V2x, V2y. And then when we look at what we put in here, if we put in A, B, C, D, we'll get A V1x plus B V2x is just W1x. Then we'll get A V1y plus B V2y. Wait a minute. Okay, and then we just W2y. W1y. Yes, W1y. And then we'll get C V1x plus D V2x, that's a W2x. And then we will get C V1y plus D V2y is W2y. And now we're in great shape. Because now if we take determinants, determinant is plus or minus 1. We've chosen this so the determinant is 1. So that means determinants are equal. And so this is just, expanding things out. And that proves the claim. Does this mean all we have to do now is check the determinant?
No,
Why not?
because you can have matrices, two matrices which have the same determinant but don't have the same lattice.
Oh, that would be unfortunate. Can I erase this board? So if your claim is true, that you can have matrices with the same determinant that generate a different lattice, what kind of condition have we just proven?
And only a condition, or
Only if is one way of saying it. What's the other way? It's this but not this.
Necessary, but not sufficient.
It's a necessary but not sufficient condition. You know, it's like, if I want my sequence to converge, the terms must go to 0. But the terms going to 0 is not sufficient to ensure convergence. It's just a necessary ante. So claim determinants equal not enough to prove lattices the same. So can you give me an example? What would you try for one of our bases?
The identity.
The identity. So let's try E1 and E2. So all we have to do, this is the nice integer lattice.
You can do pi E1 and 1 over pi E2. And that has to go in 1.
Pi E1 and 1 over pi E2. Perfect. So that will work. Can you give a more exotic example? This is a great example. It works. I have nothing against the example, but they at least look structurally the same.
The hexagonal lattice.
So let's try the hexagonal lattice. So and so on and so on. Okay, so now the question is, what do we choose for our vectors?
I think it would be 1, 0, and a half, 3, 3.
So if we do 1, 0, that means this is a unit vector. This would be a unit vector. But will their determinant be 1?
You need to scale it a bit, but
I'm sorry, no, so we would have to scale it a little bit.
Yeah.
So let's scale it by some factor r. And then this would be 1/2, and then root 3 over 2. I will trust you that I put them in. Yeah, that's definitely the right way to put it. And I'll put in a factor of r as well. And so the determinant is going to be r squared times 1, 0, 1/2 root 3 over 2, or r squared times root 3 over 2, if I've done the calculation correctly. And so if we just choose r appropriately, they will have the same determinant. Is it possible that we could have one equivalent to the other? So could we have some kind of transformation in SL2Z that would take us from one to the other?
no.
Why not?
Because SL2Z is a group, and then if you could, then you multiply something outside the group with something inside the group to get something inside the group, like
Irrational.
because this is irrational.
Good. So,
Actually, it's not in the truth.
so we're basically saying r is equal to 2 over square root of 3, and then take the square root of that. if we've done the calculation right. And so if there was such a matrix, if we applied it here, we would get this lattice point. And even when we multiply by r, that's going to have an irrational coordinate. So gamma, or like E1 and E2 would have to have rational entries, or integer entries. Is there another way you would like to say they clearly can't be the same lattice? It doesn't have to be something that you can mathematically prove, but looking at them, is there something that makes you say they can't be the same?
Like how many closest neighbors each one has?
Good. How many closest neighbors? This one over here has exactly 4 closest neighbors that are exactly 1 unit apart. Over here, this has 6. If there was some equivalence, would closest neighbors have to stay closest neighbors? Is that invariant or is that not invariant? The whole idea is to try to find quantities that do not change when you change the basis. And here we have 6 closest neighbors. We don't have that in the other one. You also want to just say, come on, you see triangles here, you see squares there. A square is not a triangle. It's, can we quantify that? Okay. So rather than starting what a dual lattice is today, given that we have a small amount of time left, I want to do an example from physics. I will risk doing this, but it's one of the most brilliant ideas I have seen in my life. Have I talked to you about why length cannot contract perpendicular to motion in special relativity? Okay, beautiful. How many of you have ever seen the mathematical formula? I'm not going to go into all the details there. I might have shared with some of you a quote from a physics textbook that I read in high school that was funny at the time, but the older I get, the more reasonable I see the quote is. And in trying to explain how so many results in special relativity are counterintuitive, the book remarked you have to remember most people don't have experience traveling at 3/4 the speed of light. I loved the word most. And I was quite curious, who actually does have experience traveling at 3/4 the speed of light? But the reason this is so important, the reason I wanted to work this somewhere into this course, is that there is such a tendency to take the data that you have and to extrapolate, and the conclusions that you are making based on the data to insist that they hold in regimes where you have no right. In classical Newtonian physics, when people did experiments, when they did observations, they basically noticed speed is additive. So if you're on a train traveling at 100 miles an hour and you're running on that train at 10 miles an hour, then it looks like to somebody on the ground that you are moving at 110 miles an hour. It's not quite right. It's a little bit different. And one of the big things in special relativity is that as you're traveling, it contracts in the direction of motion. It does not contract perpendicular to the direction of motion. There are also issues with mass, there are issues with time, there's a lot of stuff that goes on. And if memory serves, the conversion factor is something like the square root of 1 minus v1 over c, v2 over c, where v1 and v2 are the two speeds. Anybody know roughly what the speed of light is?
300,000.
Okay, so 300,000 what?
Kilometers per second.
Well, which is it? Is it meters or kilometers?
Kilometers.
Okay, so it's 300,000 kilometers per second, or it's about 186,000 I think, miles per second, which looks like about right, I think. Because if you multiply by 0.6, you get, so it's something like that. 186,000 miles a second is fast. I think some of our space probes might have gone up to what, 25,000 miles an hour. There's 3,600, is that about right?
Sure.
So if somebody at home wants to just Google, fastest man-made thing ever, if it's 25,000 miles an hour, and there's 3,600 seconds in an hour, and 25 goes into this about 7 times. So you're talking about 36, call it 40, call it about, 280, like 1 over 280,000th the speed of light. Extremely small. So these are such small corrections that for the most part we don't have to worry about it. So a lot of our talk today was to try to find something that is unchanged as we go from one coordinate system to another. This has connections to physics. And so now we'll go to relativity and Einstein. I may have his autograph. I will comment about that once the recording is stopped. So one of the rules that Einstein postulated is that physics should look the same in any two frames that are traveling at a constant speed between them. So I can always assume that I'm at rest, and if you have your inertial system traveling at constant speed, we should see the same physics. If we're accelerating, a whole different world. And that's where general relativity comes into play, very different, but two physical frames where one is just a constant speed of the other should see the same physics. So in particular, and this is always done with trains, imagine you have a train going forward on train tracks. And let's say it's going forward at 3/4 the speed of light. But it's a fixed speed. And you have a person waving on the platform who's at rest. They should see the same physics. Imagine length contracts perpendicular to motion. If length decreases or increases perpendicular to motion, what happens? Without loss of generality, we only have to study one of the two cases. If I can show you that it can't contract, similarly it can't expand by just flipping the roles. Or just do the argument again. Do you want to assume length contracts or expands? All right, so length contracts. So this person is here, and he sees the train, and it contracts. What should happen to the train? This train that's going down. You need to know a little bit of how trains work.
The train also sees the other person moving through.
Well, but what happens to the train?
It'll go off the rails.
It'll go off the rails. If the train contracts, it goes off the rails. So just to make it a little bit easier, we have two paint cans. So when the train is at rest, it's just putting paint down on the track. Maybe this is a magic train from the same person that gave Jack the Beanstalk, and it will go even if it's a little bit off the track. It's going at 3/4 the speed of light. I mean, come on. If length contracts perpendicular to motion, then as it's traveling, it's going to be putting the paint inside the tracks. However, from the point of view of somebody on the train, the person in the tracks are moving. Right?
Oh, so the tracks is gonna.
So the tracks would contract.
And the paint's outside.
And the paint is outside. They can't both be inside or outside. So after this goes on for a while, either the train slows down, or if you want, it hits a wall, which forces it to stop. I think it's better to slow it down, and then they can compare. And you're not going to have the paint magically migrate. So these are called thought experiments, Gedanken experiments. Absolutely wonderful in terms of the power that they can have. Trying to think what is fixed from different observers. And for what we're doing, instead of changing by my one initial system to another by some kind of transformation, I'm changing from one basis to another. And I want to ask what is the same. And so we've just shown that the determinant is the same, which is the area of the fundamental parallelogram, or hyperparallelogram if we're in higher dimensions. All right, so this is a good place to stop for today.